Dearly beloved, we are gathered here in the presence of God in order to discuss abstract mathematics. What an amazing, wonderful thing this is to do. So we're going to jump right into it, and glad that you're here. So let's pray. Father, in Jesus' name, we thank you for being able to gather together like this, Lord. We've thanked you for it for many times, but you just continue to grace us with the ability to continue in class, to finish well. And Father, I pray that every student will do exactly that. I pray, Father, that you will eliminate any kind of fear that may be in any student because of this COVID-19 virus. Because, Father, your gift to us is power and love and a sound mind and not the spirit of fear. So we thank you, God, for your promise. We stand on it and we refuse fear. In Jesus' name, amen. All right. Don't be afraid of abstract math either. We're going to start right off with a definition. We're going to be talking about powers of things today. So definition, this is actually 5.12, I believe. Let x be a real number and let n be a natural number and assume that x is not 0. Okay? Then we're defining 0 to the n to be 0. So 0 to any natural number power is itself. B, x to the 0 is 1. And notice, by the way, that x is not 0. 0 to the 0 is undefined. C, x to the n is defined as x times x to the n minus 1. And notice, by the way, this implies that x to the 1 is x, because x to the 1 is equal to x times x to the 1 minus 1. That's x to the 0, but x to the 0 is 1, so x to the 1 is equal to x. And part D, x to the negative n is the nth power of the inverse of x. Okay, so that's those are definitions. Those are not things that we have to prove. But here comes some things that we have to prove. Here's theorem 5.13. If a is some real number other than 0, n is some integer other than 0, then a to the negative n is the same as the inverse of a to the n. Now you're thinking, wait, isn't that what I said here? No, it's not. X to the negative n is the nth power of the inverse of x. But it's also the inverse of the nth power of x, or a in this case. So we want to show that those are the same. So proof. We're actually going to do this in cases. Case 1. Case 1 is going to be if n is greater than 0. Now, if n is an integer, it's either greater than 0 or less than 0, so we're going to have two cases, obviously. If n is greater than 0, then we're going to do this by induction. If n equals 1, then a to the negative 1 equals a to the 1 to the negative 1 And that is since a to the 1 equals a. A to the 1 equals a, so this is a to the negative 1. Okay, so the n equals 1 case is easy. I want to put a note. You can put that anywhere you want. A to the minus n equals a to the n to the negative 1 means that a to the minus n is the reciprocal of a to the n. Okay, so just a reminder, because we're going to use that a little bit later. But now, we know that the thing is true for n equals 1, so suppose that the statement is true for some m greater than 0. So suppose, for induction, suppose the statement is true for some m. We're on planet M now. What statement is that? Well, the one in the theorem. A to the minus m is equal to a to the m inverse. And we know it is true for some m because it's true for this one. Okay, so assume it's true for some m. And now we have to go to planet m plus 1. So we do the left-hand side for m plus 1. A to the negative quantity m plus 1. Okay, now let's multiply this by a to the m plus 1. Why? Because if I multiply this by a to the m plus 1 and I get 1, then I know that a to the minus m plus 1 is the reciprocal of a to the m plus 1. And so that's what this statement means. So I'll have my statement. Let's see if we get what we want here. This is equal to a to the minus 1 times m plus 1 let's see. Is that the way I want to do this? Let's do it a little differently. This is a to the minus 1 to the m plus 1 power, because that's the definition, definition D. I'll tell you what, let's erase the a to the m plus 1 for now. A to the minus m plus 1 is equal to the a to the negative 1 to the m plus 1 power. That's by definition part D, okay? So, now we'll write what I had before. A to the minus quantity m plus 1 times a to the m plus 1 is equal to, like we said here, a to the minus 1 a to the minus 1 to the m plus 1 power times a to the m plus 1, which is equal to a to the minus 1 times that same thing to the mth, because it's a to the minus 1. Remember, when you're on planet m plus 1, you want to look back at planet m now and split that off. And this, of course, is times a to the m times a. Okay. Well, that's equal to A inverse times a to the minus 1 m, a to the m, a to the minus 1 to the m times a to the m times a, and that's equal to a to the negative 1 times, now by induction, not yet, this is a to the negative m just by part D. This is a to the negative m times a to the m times a. That's definition part D again. And that's equal to a to the negative 1 times 1. Because that's the induction hypothesis, that a to the minus m is the inverse of a to the m, so that's equal to 1 times a, and so that's a to the negative 1 times a, and of course that's 1. So, what does that mean? That means that a to the negative m plus 1 is equal to the inverse of a to the m plus 1, which, go back to the statement now, that's exactly what I wanted to prove. All right, so that takes care of that. But that was case 1. All right. Case 2. Suppose that n is negative. A typical trick here. If n is negative, then let, say, k be negative n. So k is positive. So then k is positive. So by case 1 applied to k, a to the negative k is equal to the inverse of a to the k. So a to the n is equal to a to the minus n to the negative 1 power. Therefore, I can do it here, a to the n times a to the negative n is equal to 1. Hence, a to the negative n is the reciprocal of a to the n, i.e. a to the negative n is equal to the inverse of a to the n, even if n is negative. And so that ends the proof of theorem 5.13. I stick really closely to my notes on this stuff because it's easy to get off track with the negative n's and the inverses and all. So off we go, erasing the board to do yet more miraculous stuff. Theorem 5.14. And it goes like this. For every real number a squared is greater than or equal to 0. That's something that we all knew for many, many years. But that's something that is a property of the real numbers that has to be proven. So let's do that. if a equals 0, a squared equals 0, so a squared is greater than or equal to 0 holds. So we may assume a is not 0. Now, there's the trichotomy law for real numbers that says that a number is either 0 or positive or negative. So then, a is greater than 0 or a is less than 0. So case 1. Case 1 is if a is positive. If a is positive, then by the multiplicative property we did several days ago, a times a is greater than 0 times a, so a squared is greater than 0, which is what we wanted. Case 2, suppose that a is negative. Then by our old pal, theorem 5.10, negative a is greater than 0. If a is less than 0, negative a is positive. Therefore, by case 1, what? Negative a squared, negative a quantity squared, is greater than 0. But negative a quantity squared is negative 1 times a squared, which is equal to negative 1 squared times a squared. But negative 1 squared is 1, so that's equal to a squared. And since negative a quantity squared is greater than 0, a squared is greater than 0. And that's the end of that. So most of these are easy to prove, but they do require proof. On we press. I wouldn't have to erase the board so often if I wrote smaller, but then if I wrote smaller, it might be a little harder for you to see. So I suppose it's better that I do a little bit more work and make it worthwhile for you. Theorem 5.15. This one's really easy. If a is in the interval from 0 to 1, open on both ends, then a squared is less than a. So if you have a fraction, 1/2, for example, 1/2 squared is less than a half. Anything between 0 and 1 has that property. It's very easy to prove. It's a one-liner. Multiply a is less than 1 by a. So a squared is less than 1 times a, which is equal to a, and that's the end of the proof. Aren't those your favorite kind? Now, to do the next one, I'm going to remind ourselves about theorem 5.13. Let's recall that. It's going to be handy. It's that a to the negative n equals the inverse of a to the n. Okay. So just a reminder that it's going to come in handy a few times here as we prove theorem 5.16. If a is a non-zero real number, and m and n are integers, then two things are true. Number one, a to the n times a to the m is a to the n plus m. The second thing is that a to the n, that quantity to the mth power, is a to the nm. So those are the two things that we want to prove. Case one. Let's take care of the simple case first. If either n or m is 0, we may assume it's m. It doesn't matter which one. We may assume that m is equal to 0. Then, let's do number 1. A to the n times a to the m is a to the n times a to the 0, which by the definition is a to the n times 1, which is equal to a to the n, which equals a to the n plus 0, which is a to the n plus m. So in case that one of them is 0, the thing is trivial. Okay. The second one, in case one of them is 0, in this case we're choosing m, a to the n to the m is equal to a to the n to the 0. We're assuming m is 0. But that's equal to 1. And so that's equal to a to the n times 0, which is a to the nm. So if either one of them is 0, the whole thing is trivial. We know we're done. Okay, so from now on, we may assume that both of them are not 0. Okay, let's see. Case 2. Well, that's a good thing to follow case 1. All right, case 2. Suppose that n and m are both greater than or equal to 1. They're both natural numbers. And we will proceed by induction on, I could pick either one. We'll do induction on m. Okay. Let's see. The m equals 1 case is a to the n to the 1 equals a to the n times 1. But from our definitions, we know that a to the n times 1 is just a to the n. And that's equal to a to the n. So we know it's true for n equals 1. M equals 1, sorry. Okay, so now, suppose the statement is true for some m. Okay, so part 1, we now want to visit planet m plus 1. So we take a to the n times a to the m plus 1. And then once you're on planet m plus 1, you want to revisit planet m looking back. So this is a to the n times a to the m times a to the 1, which is equal to a to the n times a to the m, associative law, times, and of course by the definition, a to the 1 is equal to a. But now by our induction hypothesis, a to the n times a to the m is equal to a to the n plus m, and then, oh yeah, times another a, and that's equal to a to the n plus m plus 1. But now I can use the associative law of addition here, and this gives me what I needed, a to the n plus m plus 1, the m plus 1 case for this result. That's part 1. Part 2, the one where I take the product of the exponents, well, a to the n times, to the power of m plus 1. We're doing the planet m plus 1 because we know that the other one is trivial. A to the n to the m we've already done. So that's equal to a to the n to the m times a to the n, another a to the n. So a to the n, that quantity to the m plus 1, is m of them, a to the n to the m, and then times another one, a to the n. But that's equal to, by the induction hypothesis, a to the nm times a to the n. And I know here I can use the addition property from part 1. This is a to the m plus n, which is equal to a to the n, I can factor out the n, m plus 1, and that's the multiplication property that I needed. So both part 1 and part 2 are finished in the case that n and m are both positive integers. Case 2. Oh, I know, case 1, this was case 2, case 3. Yes, 3 comes after 2. That's good to know. It's been a while, but you know, it's like riding a bicycle. You never forget that 3 comes after 2. Suppose that n and m are integers where one of them is positive and one is negative. Now, by symmetry, we may assume that n is the positive one and m is the negative one. Okay? Then we apply, typical old trick, we apply case 2 above to the positive integers n and negative m. So this is going to take a little bit of room, so I'm going to erase the other board. Hopefully you're writing fast enough that you get a board copied down before it gets erased. I'm looking into the possibility of doing these lectures from a place with a much bigger board. I'll be doing a little more driving, but I think it'll be worth it. So we'll see. If not, you're stuck with these boards for the rest of the semester. Okay. Well, part one. If n is positive and m is negative, then assume that n is more positive than m is negative. In other words, assume that n plus m is a positive number. Okay? The reverse case will follow. From theorem 5.13, the negative case. Now by case 2, of theorem 5.13, a to the n times a to the m. Let's see, is that the theorem that I wanted? Yes. A to the n times a to the m is equal to a to the n plus m minus m times a to the m. Okay, because a to the n times a to the m minus m, of course, is 0, so I haven't really done anything here. But it'll come in handy to look at it this way. This is equal to a to the n plus m times a to the minus m, there's where that theorem comes in, times a to the m and that, of course, is equal to a to the n plus m, which is what I needed to get. Okay. The second part, part 2, a to the n to the m is equal to, now remember, m is a negative number. But I still want to show that a to the n to the m is a to the nm. So this is equal to a to the n to the negative of minus m. Now, nobody would argue with that, right? M is the negative of its negative. But now that's equal to 1 over a to the n to the minus m. And this is by definition part D, at definition 5.12, part D. That's the reciprocal of a to the n, the minus mth power of the reciprocal of a to the n. And this is equal to 1 over a to the minus nm by theorem 5.13, which is equal to a to the minus nm reciprocal, the reciprocal of a to the minus nm. But this, by theorem 5.13, is equal to a to the nm by that same theorem. So in case one of them is positive and one of them is negative, we're still okay. All right. Finally, case 4. If both n and m are less than 0, this is left as an exercise to you. So I got 3/4 of it, you do the other 1/4. This is left as an exercise. But that's the end of this theorem. Okay. Now we're going to go to a different place. We're going to talk about absolute values. Absolute values have the property, in my humble opinion, that everybody knows what it is and nobody knows how to say it. If I were to ask you what's the absolute value of 3, everybody would say 3. If I said what's the absolute value of -3, everybody would say -3. But if I were to ask you what is the absolute value of A, then people start to, well, it's the positive A. No. The absolute value of A is not the positive A, because the positive A would be A, and if A is negative, that ain't true. So people have trouble stating what the definition of the absolute value is. Now, there are 2 ways to approach this. One way is to say, well, the absolute value of A is the square root of A squared. And that's a good definition. It's the square root of A squared. Because if I take my example 3, the absolute value of 3 is the square root of 3 squared, which is the square root of 9, which is 3, bada bing, bada boom. And if I take the absolute value of -3, the absolute value of -3 is the square root of -3 quantity squared, which is the square root of 9, which is +3. So it works just fine. But for people who are a little concerned about the square root of -3 squared being +3, they need to remember, first of all, what the definition of the square root is. But secondly, to avoid that complication, we can define the absolute value in multiple ways, depending on whether A is non-negative or negative. So that's the approach we're going to take, because it's a lot easier to handle. All right. Definition. It's 5.17 if you're counting, but for all A in R, all real numbers, the absolute value of A is equal to the following. A, if A is greater than or equal to 0, and negative A, if A is less than 0. Now, I want to spend a little bit of time on this. This is probably obvious. You've probably seen this definition back in junior high school, but I still want to belabor it enough to where maybe we're not beating a dead horse, but the horse is probably sick. The absolute value of A is A. If A is non-negative, nobody would have any trouble with that. If A is non-negative, you leave it alone. Okay? But then they look at this and they say, well, if A is negative, it's -A. Isn't that a negative number? No. If A is negative, negative a is positive. And so I want to make sure that that's clear to everybody. So I could do that by saying it 4 times, but the other way would be for me to say it 1 time and then have you keep watching this video. If a is a negative number, then minus a is a positive number. And so that would be the absolute value. So what's the absolute value of negative 3? Well, do I look at the top or do I look at the bottom? For negative 3, I look at the bottom. Absolute value of negative 3 is minus negative 3, which is 3. Okay? So just having a minus sign out in front doesn't mean the thing is negative. It depends on what the sign of the thing is. If minus 3 is the one I want the absolute value of, then minus 3, which is 3, is its absolute value. Okay, the horse is not only sick, he's in a coma, so I'm going to leave him alone now. Theorem 5.18. Let m be some number that's greater than or equal to 0. Then the absolute value of a is less than or equal to m if and only if negative m is less than or equal to a itself, no absolute value, less than or equal to m. Proof. Well, you're used to this already. Case 1. If a is greater than or equal to 0, the absolute value of a equals a. That's this part of the definition. Therefore, absolute value of a is less than or equal to m if and only if a itself is less than or equal to m. Furthermore, I reverse that inequality if I take the negative of a. So negative a is greater than or equal to m. Let's see. A is less than or equal to m. Furthermore, do I need that? So, yeah, I don't think I need that in this case. I'm not concerned about that. Just a is less than or equal to m. Okay? And also, a is greater than 0, which is greater than, a is greater than or equal to 0, which is greater than or equal to negative m. So, negative m is less than or equal to a. Therefore, negative m less than or equal to a is less than or equal to m. That's all I need. I need that other thing for case 2. If a is negative. If a is negative, then the absolute value of a is negative a from part 2 of this definition. Okay. Therefore, the absolute value of a is less than or equal to m if and only if negative a is less than or equal to m. Okay. Therefore, multiplying both sides by negative 1, a is greater than or equal to minus m, so I get that part already, i.e. minus m is less than or equal to a, so I've got half of it already. But since a is negative, a is less than 0, is less than or equal to m, because m is positive, or not negative. So again, we have negative m is less than or equal to a, and a is less than or equal to m. Okay? I don't think there's anything else to do here. I think I've only done half of the argument. Yeah, I did show if and only if for the first of the steps, but I didn't show if and only if for the following steps. So I'm going to do the only if part, or actually the if part. So now, suppose we have the second part, that minus m is less than or equal to a is less than or equal to m. Then that means that a is less than or equal to m, and a is greater than or equal to minus m. So a is less than or equal to m, and minus a is less than or equal to m. They're both less than or equal to m. So the absolute value of a, whichever it is, positive or negative, it doesn't make any difference. Both of them are less than or equal to m, and that is the end of the proof. Okay, thanks for letting me finish that. The next theorem is also very familiar to you. It's called the triangle inequality. The reason it's called the triangle inequality is because it says that the length of a hypotenuse is less than or equal to the sum of the lengths of the sides. And of course, it's strictly less than if the thing is an honest to goodness triangle, if there are three sides. If it's equal to, then they're only, the whole thing collapses. But the strict algebraic statement is that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Not hard to prove once we have this. So let's chip away at that guy, and then we're going to do an example or two, maybe two. Theorem. This is 5.19. But everybody calls it the triangle inequality. And it says, for all a and b real numbers, the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. Here comes the proof. Let m, now this is proof by sneaky trick. I'm going to choose my m. I'm going to choose my m to be the absolute value of a. Then, by the previous theorem, by theorem 5.18, negative m, which is absolute value of a, negative m, is less than or equal to a itself, which is less than or equal to m, which is absolute value of a. Similarly, negative of the absolute value of b is less than or equal to b is less than or equal to the absolute value of b. Now add these. The left-hand side, I get negative absolute value of A plus a negative of absolute value of B. So that's the negative of absolute A minus the absolute value of B. That's less than or equal to A plus B. And that's less than or equal to absolute A plus absolute B. But this is the thing on the left is the negative of the thing on the right. Therefore, the negative of absolute A plus absolute B is less than or equal to A plus B, is less than or equal to the positive of absolute A plus absolute B. And so by theorem 5.18 again, I get that the absolute value of A plus B is less than or equal to this. So by 5.18 again, absolute value of A plus B is less than or equal to the absolute value of A plus the absolute value of B. Bada bing, bada boom. Okay, so that was easy. Let's do an example. Let's solve some inequalities here. Example. Suppose that x lives in the interval from -1 to 2. Prove that the absolute value of x squared plus x minus 2 is less than or equal to 4 times the absolute value of x minus 1. Now, how shall we prove this? Well, let's factor x squared plus x minus 2. This is the same as the absolute value of, now how do I factor x minus 2, x squared plus x minus 2? Of course, I need an x in the first slot of each, and then in the last slot, two numbers that multiply together to give me -2 and add together to give me +1 have to be +2 and -1. So this is less than or equal to 4 absolute x minus 1. Okay. But the absolute value of the product is the product of the absolute values. So the absolute value of x minus 1 times the absolute value of x plus 2 is less than or equal to 4 times the absolute value of x minus 1. Okay? There's one little problem. I'd like to be able to cancel the x minus 1s, but I can't cancel things that are 0. If x equals 1, and by the way, x equals 1 is in this interval, so I do have to worry about this. If x equals 1, then the left-hand side to this is 1 plus 1 minus 2, which is 0. Is that less than or equal to 4 times 0? Yes. So we may assume that x is not 1. Everything works out if x is 1. If x is not 1, I can cancel these. So then I get absolute value of x plus 2 is less than or equal to 4, which by theorem 5.18 is the same as -4 is less than or equal to x plus 2 is less than or equal to 4. Okay? So negative, if I subtract 2 from both sides, negative 6 is less than or equal to x is less than or equal to 2. And these are all if and only if. But x is in negative 1 to 2. So the last statement is true. Negative 6 is less than or equal to x is less than or equal to 2 is true, since in fact, negative 1 is less than or equal to x is less than or equal to 2. So this is true, so this is true, so this is true, so that is true, so this is true. Therefore, my statement is true. All right? There's another way to see this, by the way, without going through this part. If you wanted to be a little fancy, when you get to here, then you can say now, for all of the x's in here, I get a positive result. Because the only time that this becomes 0 is at negative 2, and that's way out of the interval. And if I use a little bit of calculus, the derivative of x plus 2 is 1. Since the derivative is positive, the function is monotone increasing, its slope is 1. And since this is increasing, it's going to be the biggest when it's at 2. And even at 2, this figure is less than or equal to 4. So it's always less than or equal to 4 for x's in this interval. So that's another way you can do it, if you don't mind using a little bitty bit of calculus. Let's do another problem. As soon as I get my fix. Okay. Another example. If the absolute value of x minus 1 is less than 1, prove that the absolute value of x cubed plus x minus 2 is less than or equal to 8 times the absolute value of x minus 1. Now, what am I going to do here? Well, before I factored the thing on the left, let's do that again. Now, how do you factor a cubic? One way is to use polynomial division if you knew what to divide by. But how do we figure out what to divide by? Pardon me ending that sentence with a preposition. A little hint that I gave you, many weeks ago, is that if I plug a number into a polynomial and the polynomial spits out 0, then x minus that number that I plugged in is one of the factors of the polynomial. If I plug in a number into a polynomial and it spits out 0, then x minus that number that I plugged in is a factor of the polynomial. So, what is one obvious thing that I can plug into this polynomial to give me 0? How about 1? 1 plus 1 minus 2. 0. So x minus 1 is a factor. So I can take x cubed plus 0x squared plus x minus 2, and I can divide it by x minus 1, and I know it's going to come out even because x minus 1 is a factor of this beast, right? So let's do the arithmetic. What do I multiply by x to give me x cubed? And the answer is x squared. I multiply x squared by everything that's here. So I've got x squared times x is x cubed. I've got x squared times minus 1, which is negative x squared. And now I subtract. Talk to yourself in this step. X cubed minus x cubed, of course, is 0. That goes away. 0x squared minus negative x squared is x squared. And I bring down the next thing. What do I multiply by x to give me x squared? The answer is 1. 1 times, I'm sorry, no it isn't. The answer is x. Duh. X times x is x squared. X times negative 1 is negative x. X squared minus x squared, and the people all said, poof. X minus negative x is 2x. And I bring down the next thing. What do I multiply by x to give me 2x? That one's easy. 2 times x is 2x. 2 times negative 1 is negative 2. Of course, I get 0, and I knew I was going to get 0 because it had to come out even. So the statement, this statement, the original one, is equivalent to x squared plus x plus 2 times x minus 1, absolute value of each, is less than or equal to 8 times the x minus absolute value of x minus 1. Okay, so this statement is the same as this statement. Now, I'd like to cancel the x minus 1s, but once again, I have to be careful. I have to make sure that I can't cancel zeros, so I have to make sure that when x minus 1 is 0, that the statement is true. Well, if x equals 1, then the statement is 0 is less than or equal to 8 times 0, which is true. So it works out if x minus 1 is 0. So now we may assume that x does not equal 1. And since x does not equal 1, this thing is not 0. I can cancel it since it's on both sides. So we must show that x squared plus x plus 2 in absolute value is just less than or equal to 8. If I show this, then I've shown that, which is equivalent to the original statement, and so we'd be done. Okay? So how do I show this? There are a couple of ways that we could do this. But notice that this function, where are the x's? There are two ways that come to mind to do this. Which way did I do it before? Okay, that's the way to do it. That's simpler than using calculus. Let's take a look at the quadratic formula. We can't factor this, But let's look at the quadratic formula. Where does x squared plus x plus 2 equal 0? And the answer is x equals minus 1 plus or minus the square root of 1 squared minus 4 times 1 times 2, all divided by 2a, which is minus 1 plus or minus the square root of negative 7 divided by 2. And for real numbers, this doesn't exist, and x is a real number. So the answer to this question is never. It never equals 0. Well, then is it positive or negative? Well, plug in any number you want, it's always going to have the same sign, because if you plug in one number and this polynomial comes out positive, and you were to plug in another number and it comes out negative, then by the intermediate value theorem you learned in calculus, someplace in between it's got to be 0, and it's never 0. This is never. Okay, it's never 0. So it's either always positive or it's always negative. So plug in your favorite number. Plug in 1. 1 plus 1 plus 2 is a positive number. So the absolute value of this thing is itself. I can remove the absolute values. So x squared plus x plus 2 is always greater than 0. So we solve. So we want x squared plus x plus 2 to be less than or equal to 8. Now, for x's in this interval, let's see what is in this interval. If the absolute value of stuff is less than 1, then by that theorem 5.18, we know that minus 1 is less than stuff is less than 1. And if I add 1 to everything, I get that 0 is less than x is less than 2. Okay? Now, suppose that I take the derivative of this function. Okay? The derivative of this function is 2x plus 1 plus 0, 2x plus 1. And if x is always positive, then 2x plus 1 is positive, so the function's monotone increasing. And if it's monotone increasing, then it's going to be biggest at the right endpoint. In fact, it never even gets to that endpoint. So x squared plus x plus 2 is less than 2 squared plus 2 plus 2, which is equal to 8. So my polynomial is less than 8, which gives me this, which gives me that. So I've proven that the statement is true. Okay? So these are kind of fun. You may actually get some to practice, who knows? Now the next topic. The next topic has to do with roots. We've talked about powers of real numbers. Now we're going to talk about roots of real numbers. Square roots, cube roots. We've learned a lot of things in junior high school and in high school about roots. For example, you've learned that no matter what positive number n is, the nth root of 0 is 0. In other words, what is a number whose nth power is 0? And of course, the only such number is 0 itself. So the nth root of 0 is 0. We also learned that if you have a positive number, then the nth root of that number is a positive number. And there's only one. Now, that's because we're dealing with the real numbers. If we were to allow complex numbers, then there are lots of roots, nth roots of a positive number. As a matter of fact, there are n of them. In fact, the complex numbers don't care if the number is positive or negative. The equation x to the n equals b, where you're looking for the nth root of b, well, that's a polynomial of degree n, and in the complex numbers, that has n roots. And in fact, they're unique roots. There's a formula called Euler's formula, which says that that if I take the number e and I multiply it to the power of I t, where t is a real number and I is the complex number square root of -1, then that thing just starts wrapping around the circle. And where t is 0, it's over here at the right, at 1, the real number 1. But as the angle increases and goes all the way to 2 pi, it comes back to 1 again. And no matter how many times it goes around, it keeps going back to the same places. That Euler's formula is that e to the it is the same as the cosine of t plus I, square root of -1, times the sine of t. Cosine t plus I sine t is e to the it, which explains, by the way, that circle. But we're not going to get into it. But what happens is if you have those nth roots, say nth roots of 1, how many nth roots of 1? Well, if you're looking in complex numbers, then the square root of 1 is 1. But with complex numbers, you also consider -1 to be a square root of 1. If you have a cube root, then instead of going from 1 all the way to -1, it goes 1 and then it goes 120 degrees to the next root, 120 degrees to the next root, another 120 degrees back to the original one, and you get all nth roots by subdividing that circle. It's a fascinating topic that we're not going to do. But with real numbers, we're going to handle all these properties of roots, and we'll start that next time. Until then, God bless you, stay safe again, and hope to talk with you soon.